So what I'd like to talk about today is fault tolerance with LDPC codes, and I'll explain what an LDPC code is. So this is going to be kind of an overview, mostly of work that's been done in the past few years by people other than me. Although I did do one thing that kind of kickstarted this area, and so I'll talk about that as well. And because it's an overview and touching on a bunch of things, it's going to be fairly light on technical detail, but I'm happy to try to answer more technical questions if they arise. Okay, oops, how do I advance now? Okay, there we go. So the main thing that we need to worry about for the purpose of this talk is that quantum computers will probably need some sort of error correction to work. So why is that? Well, qubits are very, very small, generally, maybe single atoms or small superconducting rings. And so small things are, of course, inherently more susceptible to being bumped and changing their state than larger things. So small bits or small qubits are certainly going to be noisier than large ones. And in order to be quantum, they need to be small. So that's one factor. The other factor is that there's more things that can go wrong with a qubit than with a classical bit, right? You have not just to worry about bit flips, where 0 changes to 1, but also phase flips. 0 plus 1 changes to 0 minus 1. And one version of phase flipping is something called decoherence, which happens when the environment learns about the state of the system. And so that's something that really is unique to quantum mechanics. If you read a bit in a classical computer, that doesn't change it at all. But in a quantum computer, it does change it. And that's something that's going on all the time. Any atom in the environment can potentially learn a little bit about the state of the quantum system and therefore cause a little bit of error. And that's happening all the time. And that's something we really need to get rid of and to correct for if we want to build a big quantum computer. So the central result in the theory of fault tolerance is the threshold theorem. And the threshold theorem says in its original version that if the error rate per gate and time step is below some threshold value, the threshold piece of t is some sort of universal constant, then in that case, you can use coding with fault-tolerant protocols to reduce the error rate to arbitrarily small on the logical state. And to do so, the overhead is only polynomial in the log of the size of the computation and in the error rate that you're trying to achieve. So, okay, so what goes into a fault-tolerant protocol? Well, the first thing we need is a quantum error correcting code. So we're going to encode some number of qubits, k, in a larger number of qubits, n. And so the k qubits that we're starting with are the logical qubits. We're not actually physically encoding them, but they're going to be present in a distributed fashion in our quantum computer. And those k qubits are the ones in which we're performing our quantum algorithm. And then there's n physical qubits that are actually realized in your quantum device. And those are the ones that are experiencing error. And we want this quantum error correcting code to have the ability that, even if there's errors on a few qubits or a small fraction of the qubits, physical qubits in the quantum computer, we can correct those. And the logical qubits will be insulated and have a very low effective error rate. So two features that we want out of this quantum error correcting code is that we don't need too many extra qubits, that the rate k over n is relatively high. Obviously, it can't be higher than 1, but we'd like it to be as high as possible. And next thing, of course, is that we want it to be good at correcting errors. So when I say, some fraction of the qubits go wrong, say each qubit has an error with probability p. So then there's about pn errors in the system on a typical case. And so we'd like p to be as large as possible. But then the third thing is that we want to be able to do this and have an efficient classical algorithm that when there's an error, we can deduce what that error is and correct it, or at least compensate for it. And so people have come up with lots of quantum error correcting codes, and some of them certainly satisfy all these conditions. But the problem is that to build a quantum computer, we need to go beyond that. We also need a way of doing all the error correction procedure when there's errors in the procedure itself. And that's much harder, so that you need a fault-tolerant error correction procedure. And moreover, we need ways to do the computation without losing the protection against errors. So we need fault-tolerant gate constructions. We need to be able to prepare the initial states and other Ancillas states that we need during a computation in a fault-tolerant way. We need to measure in the fault-tolerant way. And so I think it's fair to say that most of the codes that people are very seriously considering for building a fault-tolerant quantum computer are some version of LDPC codes. And LDPC stands for low density parity check. So let me tell you what an LDPC code is and why we want it. And that's gonna, And so the LDPC code is a class in the class of stabilizer codes. I'm not really gonna explain what stabilizer codes are, but they have two additional properties. So stabilizer codes, you have a bunch of constraints that are tensor products of polys. In the LDPC code, each of those constraints, each element of the stabilizer, each generator of the stabilizer involves only a constant number of qubits. And then each qubit is involved in only a constant number of constraints. So probably many of you are familiar with classical linear coding. So stabilizer codes are kind of the quantum version of linear code. And classical LDPC codes are just saying that each parity check has only a constant number of bits, and each bit is in a constant number of parity checks. And so why do I say that LDPC codes are the leading candidates for fault tolerance? Well, the real leading candidate for fault tolerance right now is a family of codes called surface codes, and they're an example of LDPC codes. So why do we want to do this? Well, the reason is that when we do this fault-tolerant error correction procedure, it's helpful to only have to touch a small number of qubits at a time. And so LDPC codes do that. So I'll elaborate on that more in a minute, but I guess I want to comment that the reason that I don't want to just stop at surface codes is that while surface codes are very good, they have a number of good properties. LDPC codes that are not surface codes can potentially have a higher rate. And therefore, they do a better job at meeting one of those criteria that I was asking for before. So, okay, so fault-tolerant error correction. So there's kind of three main methods of fault-tolerant error correction. Some of the most efficient methods really are methods due to Steen and Nil. And the thing is that Steen error correction and Nil error correction both use very large Ancillas states. And so you have to spend a lot of work making those Ancillas states. But then once you've done that, you can very rapidly interact with the code block, the error correcting code that you're using for your computation, and extract the error information that you need. So they're actually really very good, very efficient error correction procedures. But the problem is that they use code blocks which are the same, really the same code as the one that you're using. So if you want to get an efficient error correction procedure, you're going to use an efficient error correcting code, you're going to use a very big code block. And that means that the Ancillas that you make will have to also be very big. And that means that it really is a lot of extra work in order to build those big Ancillas. So that's something that we kind of like to avoid. And so then comes the third family of fault-tolerant procedures, which is the Shor fault-tolerant error correction. So Shor is actually the first error correction procedure known in Shor's original paper on fault tolerance. And then what you're going to hear about next week, flag fault tolerance, is sort of basically a refinement of Shor error correction, which uses fewer qubits and has ways of checking errors. Anyway, so Shor error correction uses entangled states. So in the case of flag qubits, just single Ancilla qubits. And the number of gates that you need to do this for each bit of the synchron, which is to gain one bit of information about the error, is proportional to the weight of the stabilizer generators, the weight of the constraints that you have in your code. So if you have an arbitrary quantum error correcting code, an arbitrary stabilizer code, that weight would be very high if you have a large block. And so Shor error correction and flag error correction are not good choices. But if you use an LDPC code, then Shor error or error correction or flag error correction is a good choice, because the the size of each generator is small. And so we only need to touch a small number of qubits. And the reason you want to touch many qubits is because, well, if you have all of these gates and some of them are going wrong, then the odds of getting through one measurement of one bit of the synchrome without having any errors is very small. Whereas if it's a small size, then you have a pretty good chance of getting through. Now you do in your fault-tolerant error correction procedures have to take account of the fact that some of your synchrome bits will be wrong. And I'm not really going to talk about that, but that's a condition to keep in mind. But there are ways of doing that for some codes anyway. Okay, so we've decided that we want to use LDPC code. So what do we have available? Well, one code, as I said, that's very popular, or one family of codes, is the surface code. So surface code is an LDPC code which is based on a graph that's on a surface, two-dimensional surface. So so for instance, in the figure here, I've drawn a square lattice, and the qubits in this lattice are located on the edges of the lattice. And then the stabilizer generators, the constraints for this LDPC code, are based on the plaquettes, the squares, the two-dimensional faces of this lattice, and on the vertices. And they're different kinds. So each face has a constraint x, 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 x. And what that means is that the state, the code word state, has to be a +1 eigenstate of x, 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 x around this plaquette. And each vertex has a stabilizer generator z, 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 z for the 4 edges touching that vertex. Those constraints for all the vertices and all the plaquettes of this lattice define the code. The code is the set of all states that satisfy all of these constraints. And so it turns out that in this code, the logical qubits, which is also the smallest error that can change a code word to a different code word, correspond to topologically non-trivial paths. So for instance, if this surface is actually the surface of a torus, so we're connecting the opposite sides of the square, then the logical qubits are associated with loops that go around the torus in a non-contractible way. And so there's 2 different loops. There's many loops, but most of them are topologically equivalent. So there's kind of 2 inequivalent ones, well, or kind of a third one that's doing both of them. So this code on a torus has 2 logical qubits. And in general, if you do a different surface, a surface with boundaries, it's going to have a number of logical qubits that's associated to some topological property, which is basically a constant depending on how, invariant more or less on how big the lattice is. But the distance depends on how far it is to get around. And if there's n qubits, this could be an O of n to the 1/2. It's then the distance is the square root of n. So okay, so why do we like surface codes? Well, one reason is that it turns out that even though the distance is only square root of n to n qubits, it's pretty good at correcting typical errors that occur randomly. If say each qubit has an error with probability p. So that's a very good thing, because that means that the threshold error rate that we need in order to make our fault tolerance work is pretty high, like in the vicinity of 1%, if you have to polarize it. So that's good, because that sets the threshold of the code family you use sets a constraint on what the experimentalists have to do in order to make this thing work. They have to get below that threshold, otherwise error correction is not going to help and actually will hurt more than it helps. So the next really nice property of this surface code is that it has a 2-dimensional layout, right? If you do it on a torus, that's a little awkward, but if you do it on a flat surface and use some boundaries to create the topological effects, then only you can put it in a flat thing, and only nearby qubits need to interact with each other. So that's something that in a lot of systems is much easier to do than having qubits that are far apart of each other. And then finally, there's a lot of gate constructions that have been devised for the surface code. Some use code deformation, where you change the lattice to modify the way the logical qubits are done. Others, have different surfaces that you can kind of tie together by doing some operations and then cut them apart again in different ways. And you can do a lot of gates that way. And those things don't break this two-dimensional layout property, and they don't use excessive extra overhead. Now, there are some other gates that require some more overhead, and that's still a bit of a problem, but it's not one we know how to avoid in any system, really. That's not true. There's some specific codes we know that can avoid that, but they have other drawbacks, so it's kind of a trade-off. In any case, the surface codes, however, are not perfect, and so the big problem with them is that they need relatively a lot of overhead. So they satisfy this threshold theorem that I said before, which is that the scaling of the overhead is not too bad. It's a polynomial in the logarithm of the size of the computation you want to do. But in practice, for even relatively modest computations, you're going to need hundreds or thousands of physical qubits for every logical qubit. Okay, so that's kind of annoying because, well, it means that if you have 1,000 physical qubits, which sounds like a lot to a modern experimentalist, you still might only have a handful of logical qubits, not enough to do anything that's interesting in the sense of getting a speed up over classical computation. And if you can get to a million physical qubits, well, then maybe finally you're starting to get to the point where you can do something that you can do classically. So that's one problem that we'd like to overcome. And another problem, which is less serious, is that while there's been a lot of work that's gone into classical decoding algorithms for the synchron of surface codes, they're still a bit slow in practice. And so that's something that could see some further improvement, either by finding better algorithms for the surface code or by finding other codes that have better decoding algorithms. Okay, so what other options do we have? We said we wanted to use LDPC codes. So let's try to find an LDPC code that has a better rate than surface on how efficient a code that's laid out in 2 dimensions can possibly be. And so in order to do that, we're going to have to go outside of 2 dimensions. So we're going to have to give up that property. So one family of codes is actually still surface codes, but now they're not on a flat surface, they're on a hyperbolic surface. And it turns out that if you pick clever hyperbolic surfaces with weird connectivity, that you can achieve this goal of having a constant rate, k over n, as n gets large, and as the logical error rate gets very small. But the problem is that the distance in those codes is only log n. So it does increase with n, but very slowly. And that means that the logical error rate, while it's suppressed as n gets larger and larger, is only dropping polynomially with n rather than exponentially with n, which is what you normally see. So I noticed that there's some questions in the Q&A. Let's see, do surface codes allow qubit recycling? I'm not completely sure what you mean by that, but the surface codes, if you're doing, say, lattice surgery, then you might have, qubit, a logical qubit over here, and some Ancilla qubit over here encoding the surface code. You tie them together using this lattice surgery, and then cut them apart later. And then these qubits can be reset into a new Ancilla. That's certainly possible. And then second question, are there message passing decoders for surface codes or other LDPC codes as there are for classical LDPC codes? So moreover, can one use density evolution for asymptotic orthogonal? So I'm not sure what density evolution is, so I'm not going to answer that question. So there are message passing decoders that people have worked on, but there's actually a major complication. And so they don't really work as well for quantum LDPC codes as they do for classical LDPC codes. And the reason for that is something called degeneracy. So in a quantum code, you can have this phenomenon where you do some set of different errors well, some set of operations, some set of errors essentially, or bit flips or something like that to the code word and get back to the original code word. That doesn't happen classically. And what that means in terms of message passing is that you'll have different sets of errors that are equivalent. And so if you do some sort of belief propagation algorithm, it tends to get confused on these. What this translates to is you have in the counter graph, you have small loops, which is something that causes these message passing decoders to fail. And so you have to do something a bit more clever in the quantum case, but I'll talk about decoding algorithms. Okay, so
Daniel, can I ask you a very quick question?
Sure.
It's a little confusion in the Q&A. So in the definition of quantum LDPC that you gave, is being a stabilizer part of the definition? Because then towards the end of the slide, you said if you relax stabilizers, you might get better rate. I got a little bit confused about that.
Right. So yeah. So usually, I mean, I think it's fair to say that usually it's part of the definition of an LDPC code. People have also looked at codes where their ground states is some local Hamiltonian, where the Hamiltonian is the sum of terms, each of which is low weight. And so that's kind of like an LDPC code. So if each of those terms is a poly, and the Hamiltonian is unfrustrated, so there's the ground state, which is an eigenstate of each term individually, then that is in fact a stabilizer code. But if you don't satisfy both of those constraints, then it would be something that's not a stabilizer code. And there's some possibility of looking at a code like this that might have similar properties to an LDPC code. I think in most cases, people do not actually call them LDPC codes, but they might have some of these same properties that we want and still circumvent some of the difficulties we have. But in any case, there's been a lot of progress in recent years, as I'm going to tell you about, on just stabilizer codes and LDPC codes, and doing a lot better than we were doing, say, 2 years ago or 4 years ago. So, okay, so moving on to other codes. So the hyperbolic surface codes, yeah, are okay. And one advantage that they do have is that we can use the surface code decoding algorithms that we have, because it's just a surface code. But in order to do better in terms of correcting errors, we might want to do something else. And so one option that's been suggested is the 4D hyperbolic surface code. So these use a similar idea to the surface codes, where you have a lattice tiling, in this case, a 4-dimensional manifold. And it has to be a hyperbolic manifold in order to get the same high rate that we did with hyperbolic surface code. But because of the properties of 4D hyperbolic spaces, the distance is not log n, it's n to the epsilon, where epsilon is some number between 0 and 1/2. And so that's a good thing. That's much better at correcting errors in principle. But in practice, we don't have decoding algorithms that can take kind of full advantage of that distance. There's an algorithm by Matt Hastings that does decode these hyperbolic surface codes, but it gives only kind of logical error rate that's 1 over polynomial n, just like the 2-dimensional surface code. So that's not a great candidate at the moment, but if somebody comes up with better decoding algorithms, that might be interesting again. So then one family of codes, which I'm going to talk about some more, is called expander codes. And these have turned out to be very promising. So they use a construction called the hypergraph product construction. And they have good decoding algorithms. And they seem to have a reasonable threshold for error correction. So that's, and they have high rate as well. So that's something that looks like it might be the correct direction to go if we want to use high rate LDPC codes. But I would also be remiss if I didn't mention some of the major progress over the past year in LDPC codes, which is that it used to be that we could only do, no matter 2 dimensions, whatever dimensions, we couldn't do much better in terms of distance than with the surface code, right? The surface code had a distance square root of n. There were some codes that had a distance that were known that had a distance that was square root of n times some polylog n factors. But for a long, long time, that was all it could happen. But in the last year, there's been a lot of progress in getting beyond that. And now we have codes that have a distance n over log n. That's probably still an active area of research. It would not be at all surprising if that just gets up to something that's O of n. The problem is that these codes are not suitable yet for what I want to do because they have low rate. They're not designed to be high rate codes yet. But the fact that we've made this progress maybe means that the next step is to find high rate codes that also have high distance. And so those codes could potentially be much better at correcting errors than these expander codes or even than the surface code. Okay. So hypergraph product codes. So what are those? Well, again, I'm not going to get into the technical detail, but basically it's a construction that takes two classical codes and from them it produces a quantum code. And so it's some sort of product construction. Again, I can't really say too much more without going into more detail than I really want to. But there's a couple of important things about it. So one of them is that if both of the classical codes that you use are LDPC codes, so for instance, it's the one LDPC code that you use twice, then the quantum code that you get is also an LDPC code with slightly higher numbers of qubits in each row versus the number of classical bits in each row, for instance. And the other thing is that if the rate and the distance, well, if the rate of the classical codes was good, then the rate of the quantum code will also be good. And the distance behaves in a less good way, but still not a horrible way. So in particular, if you take an NKD classical LDPC code and you take the hypergraph product with itself, then you get a quantum code that has n squared plus n minus k squared physical qubits, so order n squared physical qubits, k squared logical qubits. So the rate is order k squared over n squared, which is the square of the classical rate k over n. So if the k over n was constant, then k squared over n squared is also constant. And the distance, however, is just the distance of the classical code. And so that means that the number of errors that it can correct is no larger than the classical code, but the number of qubits is increased to n squared. So, so even if the classical code was a good code, it had a constant relative distance, d over n was a constant. The quantum code is not. It just has a distance that orders square root of n. Nevertheless, that turns out to be good enough for these fault tolerance purposes in order to have a threshold. And so codes from this hypergraph product construction seem to be useful. And so one particular family of codes that's received some attention is the quantum expander codes. And so to do that, you take a classical expander code and take the product with itself. Now, the classical expander codes are good codes. So we get codes that have the quantum codes that have constant rate and that have distance square root of n. Okay, so why is it enough to have a distance square root of n to correct errors? Because again, if we have an error occurring on each qubit with probability p, then we should have p times n errors, right? And that's more than the distance. So why can we correct more errors than the distance? Well, the thing is that the distance tells you about the worst case error. And these errors, because they're occurring randomly on different qubits, are typical errors. And so if errors occur randomly, this is true in the surface code, it's also true of general quantum LDPC codes. If the error rate is low enough, below some percolation threshold, then the errors will form small clusters that are far apart from each other. And those clusters, if you're at a low enough error rate, will be small enough that the code can correct them. They'll be below the distance of the code. And because they're far apart, they don't really interact with each other. You don't get confused about how to correct them. So therefore, it turns out that actually general quantum LDPC codes have a threshold for typical errors, provided the distance is at least order log n. So that's why these these hyperbolic 2D surface codes are still useful, even though the distance is only log n. They can correct typical errors, albeit without as much error suppression as a code with a higher distance. So, okay, but remember I said that the error correction procedure itself has to be fault tolerant. And one feature of that is that when you measure a bit of the error syndrome, you measure one of these local constraints to try to figure out where the error is, that measurement itself can be wrong with some probability that's also kind of order p. So in order to compensate for that, we need a decoding algorithm that can take that into account. And that's one of the things that makes the surface code decoding hard. But again, you know, with some sort of, at least in the surface code, you can do this by adding an extra dimension. You can say, well, the surface, this is not physically adding a dimension to the code. This is in your representation of the data that you're doing. You measure the synchrome once, you measure the synchrome again, you measure it again. And so you can make a kind of a 3-dimensional plot of when and where you saw errors. And then a similar percolation argument says, oh, well, again, these have to form clusters, and therefore we can correct those clusters, figuring out where both the synchrome errors were and where the physical errors were. Okay, so in a quantum expander code, we also have robust decoding, and it's actually even better than the surface code. And so again, we have a percolation argument that says, well, errors form some clusters that are well separated from each other, and we can treat each cluster separately. But one property of the expander codes is that, well, the Tanner graph, the graph that tells you connects between the parity checks and the qubits, is an expander graph. And so that means that, you know, if you have a small cluster of errors in your code, and you imagine adding some additional errors around the outside, make this cluster a little bit bigger, well, then the number of synchrome bits that are affected by this is growing very rapidly as the synchrome grows exponentially. And so what that means is that we can do kind of a rapid, fairly greedy algorithm that tries to say, well, okay, what happens if we flip this bit? Does the number of violated synchrome checks increase or decrease? If it decreases, well, that's moving in the right direction. If it increases, that's moving in the wrong direction. And because of this expansion property, you're by looking at the correct subsets of bits to flip, you can make it shrink rather than grow, and make the error shrink rather than grow, provided these clusters are not too big, which is what you're guaranteed by this percolation argument. So this is not just an efficient decoding algorithm, but it's actually a better one in many ways in the surface code. Because in the surface code, you had to measure the synchrome many, many times. In this case, you could just measure it once. And while that's not enough to completely decode, because some of your measurements will be wrong, it is enough to get, you know, a lot of information about the errors and to mostly eliminate them. So that's kind of a much more efficient thing to do. Again, this is a fairly recent thing from the past few years that we've known that this is possible. And there's some work trying to understand, well, okay, suppose we have an expander code, a quantum expander code. What does it actually mean in terms of numbers of how well we can correct errors? What error rate does this have to be? And it turns out that the threshold for correcting errors is pretty good. It's on the order of a few percent. Now, that's not directly comparable to this 1% threshold that I mentioned for the surface code. And the reason for that is that these calculations for the expander graphs are done in a simplified model, sometimes called what's it called? Sorry, blanking on the name. Anyway, it's a simplified model where, you know, you have synchrome bit errors and you have physical errors, but you don't keep track of the total number of gates involved in the circuit. Whereas, a phenomenological error model, sorry. And so the people who look at phenomenological error models for the surface code, but they're higher. They're like, you know, order of 10%. So it's like a little bit smaller than surface code, but not dramatically smaller. Now the circuits, and this is a catch, the circuits to do this correction are probably more complicated because the checks on these expander codes are larger than the checks in the surface code. So in practice, the threshold would probably be a bit smaller if you follow this all the way through, but that hasn't really been calculated yet. So that's still an open question. Okay, so so the next thing I wanted to talk about, where there's also been some progress, is fault-tolerant gates for the surface code. Sorry, not for the surface code, for the expander codes. So there's a variety of tricks for the surface code, and some of these can kind of be imitated for these expander codes. So there's a bunch of gate constructions that work kind of with arbitrary stabilizer codes, and some of them are suitable and some of them are not. So for instance, transversal gates is I'm not going to explain what that is. If you know what it is, that's fine. But they're a very simple way of doing fault-tolerant gates. But there's something that doesn't work very well when you have a big block of a code that encodes many, many logical qubits. Because what these transversal gates do is they take a whole block and they do some gate that does a single qubit gate, so it interacts all this block with another block. And then it does something to all the logical qubits in the block. And that's not generally something we want to do unless it's some very specific situation. It's not something we want for our general algorithms. So we'll probably have to do something else for most of the gates. And again, there are things you can do, but one recent progress to try to keep the overhead of these gate constructions down is to do code deformation tricks, which are kind of similar and inspired by those used for surface codes. Okay, so however, those use just Clifford group gates, so that's a set of gates that's non-universal. So we're going to need additional gates, and as far as we know, the best way to do that is again using magic states and state injection, which is another standard fault-tolerant gate construction, and one that's also used for surface codes. Okay, but how can we do that and keep the overhead down? Well, the thing is that in order to do state injection, you require a large ancilla that's like the size of the code block. Okay, and then you interact that ancilla block with the code block that you're using. So in order to do that, we're going to need to create this special state, the magic state, encoded in a large code block. And of course, at the beginning of the computation, we also need to create a logical qubits, logical code blocks, say in the logical state 0. So how can we do that? Well, here's a way. It's probably not the best way, but it's a way that does work, which is to use one of the other fault-tolerant protocols called concatenated coding. And so what we do is we take some small code and we encode the Ancillas state that we want in this small code. So we take each qubit of the Ancilla and encode it in one block of this small code. And then we take each of those and encode them again using, say, the same code, okay, and again and again and again. And so now we have a code that uses many, many qubits, although again, it's only some polynomial in the log of n, or of the size of the circuit that we need to make the Ancilla. Yeah, I'm sorry, we don't take, yeah, what I said was wrong. So we don't take the Ancilla initially. We create logical 0 states this way. And because we have a fault-tolerant protocol for the concatenated code, then once it's encoded, we can create the Ancilla state on the concatenated code. Okay, and once we've done that, well, now we've created the encoded magic state, or whatever state we need, in the LDPC code. And so now we can decode the concatenated code. We don't need it anymore. And then we're left with the Ancilla state that we wanted. So this is a big pain in the neck. The overhead, as I said, is n times polylog n. N now doesn't have to be the number of qubits in your whole quantum computer. It's the number of physical qubits in one code block. So that would be, if we're doing that for the whole code, we kind of ruin the overhead that we were hoping to get, because we'd be using the overhead of the concatenated code rather than the overhead of the LDPC code. So sorry, I noticed there was another question here. So let's see what that is. How can one perform gates via code deformations without affecting multiple qubits in a block in a case where transversal gates would not work? Yeah, okay, so good answer, good question. The answer is that you do affect multiple qubits in a block. You affect all the logical qubits, but if you're careful about how you do it, you get to control which ones you affect. So for instance, in the case of surface codes, and it doesn't work exactly the same way in the case of LDPC codes, you have, you kind of localize, physically localize your logical qubits by having, holes. You have a surface that has some holes in it. And so for instance, you can take these holes and move them around each other. And then only the qubits associated with those particular holes have a gate done to them. Now, if you do some arbitrary deformation, you will be affecting the other qubits. And it turns out in the case of the LDPC codes, there's an element of that as well. But the upshot is you have a wide enough variety of deformations that you can do that in principle, you can do gates that will just affect single qubits. But it is an important problem in here to figure out kind of explicitly how to do that. And that's something that hasn't been done yet. Okay, so getting back to what I was saying. So we use the magic states to, we can create the magic states using this concatenated code procedure, but that procedure itself has substantial overhead. But it has substantial overhead in the size of a single block. So suppose instead of putting all of our logical qubits in one giant block of the code, we break up the computer into smaller blocks that are still large. So I'm going to use something that's a size k over polylog k, if there's k logical qubits in the whole thing. And each of those blocks uses our LDPC code. And so those blocks have a pretty good rate because they're still quite large. And then but then the overhead needed to make an ancilla for one of these blocks is k over polylog k times polylog n, which is, again, polylog k. So the polylogs cancel out. If we were smart enough to pick a big enough polynomial with a log in the denominator here, then we end up with something that's the total overhead to create one of these ancillas is smaller, or at least no bigger. Well, I guess it has to be bigger than a single code block, but it's smaller. It's still a little o of n, the total number of physical qubits that we needed for all the blocks. So in particular, it's little o of k over the rate. So asymptotically, the size of this overhead of making this ancilla is negligible. But the catch for that is that we can only make one at a time, or we'll lose the scaling. If we wanted to do things in parallel, if we wanted to make many of these ancillas, one for each code block, then we'd be back to having this polylog overhead. And so we can't do that in this procedure anyway. Okay, so that's the way that you can still have low overheads, at least in the asymptotic regime, and use these LDPC codes. Okay, so what's the upshot of that? Well, the upshot is that if you have a code with the following properties, so first of all, it has to be a family of codes that are low density parity check codes. They need to have constant rate R as n goes to infinity. So there's bigger values, bigger sizes of code that get better, not necessarily better and better rates, but rates that don't get smaller and smaller. And that the values of n that work for this code are not too rare, so that you can always find one of about the right size for your computation. And they're pretty good at correcting typical errors, even when there's synchrome errors. So in this robust error correction scenario. And when they do that, then the logical error rate goes to 0 as n goes to infinity. And let's say it goes as 1 over g of n, some function g of n. And then finally, there's an efficient classical decoding algorithm for these codes. Well, in the upshot, and expander codes, by the way, have all of these properties. That's kind of what I've been discussing. So the upshot is that there exists a threshold for computations that are of size little o of g of k computations, and the overhead is arbitrarily close to 1 over r. So what that's saying is that asymptotically, you can create LDPC-based fault-tolerant protocols that have a constant overhead, that don't have an overhead that grows with the size of the computation, but one that stays the same. And so to be a little more precise here, if you have a code family that's satisfying the first 4 conditions, then you pick some alpha less than 1. And if you have a circuit family that you want to perform that uses k logical qubits in f of k locations, where f of k is little o of g of k to the alpha, and you want to achieve an overhead within a constant factor eta of the rate of the code, and a logical error probability epsilon, then there's a threshold error rate, which depends on this eta that you want to achieve, and a threshold size, k0. And if you have computations that are bigger than k0 and scale as f of k, then if the error rate per gate or time step is below this threshold value, p sub t, then there exists a fault-tolerant simulation using the LDPC family that has logical error rate less than epsilon and overhead less than eta over r. So it can be a constant, and it can be a constant that's arbitrarily close to the rate of the family of codes that you're using. Okay, and then property 5 is needed so that the fault-tolerant simulation that you're doing only uses a polynomial amount of classical computation, which is obviously desirable as well. Okay, so so now I've said a lot about LDPC codes, and I think it's time to stop and think again, which is better, surface codes or LDPC codes? And again, there's no answer to that. It's there's advantages to one, advantages to the other. So so right now, based on the state of the art now, LDPC codes have one big advantage. They have a low overhead compared to surface codes. That's at least in the asymptotic regime. And moreover, it's not just that they have a low overhead, but there's no theoretical limit to the overhead. The overhead, by picking an appropriate family of codes, can be made arbitrarily close to 1. That there's very few extra physical qubits per logical qubit. It depends on how big on the computation you want to get and how hard you're willing to work, say, to get the error rate down. However, again, if you're stuck with the current knowledge of LDPC codes, well, the threshold error rate, while not, horribly bad, is probably going to be worse than surface codes. We don't know how to do this with local gates in a finite number of dimensions, and that seems like something that's probably very hard to do. We don't know how to do it with a fully parallel circuit. So you're really, if you have a well-parallelized algorithm, then you'd end up trading off space for time. At the moment, I think that's a good trade-off because number of qubits is a big constraint in existing systems, but it's clearly something that's not completely desirable. And right now, we could really do a lot better with the gate implementations. The ones that we have that we know they work can be pretty complicated, and some of these new ones with code deformation are not very explicit, and so that needs to be worked out better. But this is with the current state of the art, and I don't think that's a fair comparison because surface codes have been around for a lot longer, and they've received a lot of attention, a lot of optimization, and 5 years ago, LDPC codes, I had shown that this constant rate thing was possible, but most of the stuff I've talked about today just was not known. We didn't know even families of codes that could satisfy all those conditions 1 through 5. We do now. We certainly didn't know what the threshold was going to be. And while we still don't know, we have an idea that it's not too bad. And so many things have been done in the past few years. And so I think that will continue to be true. And we definitely need more work. And so in that spirit, I just want to end with a list of I think, open questions that are all like really interesting and really important. So one very big one is, suppose you run like a full fault-tolerant protocol using LDPC code. You count all the gates in the error correction procedures, you count the gates to do logical gates and all that other stuff. What is the threshold that you get for that? And how does it compare to the surface codes? And of course, you know, that's not just a single answer. It's going to depend on continued optimizations of all of these procedures. Next open question. So are there good quantum LDPC codes? So that is, are there codes where the relative rate k over n and the distance d over n are both constants as n gets large? And you know, a year ago, a lot of people might have guessed that there wasn't because we were so unsuccessful at finding high distance codes. But there's been a lot of progress in the past year, and maybe soon we'll be able to say, yes, such codes do exist. And here's the thing, is that there's a bound for channel capacity. So if you guys, well, this is not fault tolerance. If you guys want to transmit error-corrected qubits over a noisy channel, there's a bound coming from random coding. That's the best you can do using random coding. But it turns out that quantum codes can beat that random coding bound, called the hashing bound, by at least a little bit. And they do it using this phenomenon of degeneracy that I mentioned. You have different errors that do the same thing to the code, and that lets you kind of squeeze more error correction capability in some circumstances into your code. And so quantum LDPC codes, they are very degenerate codes. They have a lot of instances of different errors doing the same thing. So it's a really interesting question of can you come up with quantum LDPC codes that beat the hashing bound for channel capacity and high-rate LDPC codes. And in particular, maybe they can do it by a lot. The upper bounds are not very tight, or at least they're far away from the hashing bound. Okay, so next question. The protocols that I mentioned that have these complicated gate constructions, they only show big overhead improvements for large circuits. So are there good protocols for small circuits? In particular, circuits that we might want to implement in the next 5 to 10 years. So that's would be really interesting, because that would let us get out of the NISC error and into the fault-tolerant quantum computation error sooner. So another question is decoding algorithms. We would like to make them faster, of course. The current one is fast. It's not too bad. It has this single shot property where you don't have to measure the synchrony many times, but it probably could be made faster, and it can be improved in terms of the error threshold. And so one of those papers that I mentioned was doing that by combining it with some belief propagation ideas. And gate constructions. Clearly, this is something that we need a lot more work on. There's just been a little bit. Can we get specialized gate constructions that don't require too much overhead? And then the next two questions, it's less clear whether it's possible or not, but can we get around this problem with parallelization? If we come up with better gate constructions, maybe we can do it in a way that lets us preserve parallelism in the original algorithm. And finally, is there some way to use these LDPC codes in nearest neighbor gates in constant dimensions? Or is the overhead of getting the faraway qubits to talk to each other going to be so large that we lose the benefits of having these high-rate LDPC codes? If we can't do that, well, the LDPC codes are still interesting, but they're only interesting for architectures that allow you to easily communicate between faraway qubits. Things like photons can do that. But they'll be less good for things like superconducting qubits, where it's preferable to have neighboring gates talk to each other, neighboring qubits talk to each other via gates. So yeah, that's all I wanted to say. So thanks.
Great, thanks a lot, Daniel. That was really very interesting. Let me ask you a quick question and then turn it over to everyone else. In terms of using expander codes, there's always this question: how do you ever get the qubits to talk to each other? Is that what you meant by embedding them in finite dimensions. And so in what way would this, would this work and scale and so
on? Right. So, so getting them to talk to each other, I mean, usually, they talk to each other by gates. And the question is, which qubits need to have gates that interact the two of them directly, right? And so typically, if you have a check operator, then all the qubits involved in that check operator have to talk to the same qubit, because at some point, that information from them has to get together. Now, it could be that they talk to the same qubit before they interact, where you have some ancilla and you create some many qubit ancilla and you send it all over. But to make that entangled ancilla, those qubits had to interact as well. So you need some kind of way of doing that. And if they're physically near each other, then that's much easier than if they're physically far apart from each other. So that's what I mean by embedding in 2 or 3 dimensions, is you say, well, let me take the connectivity graph of the qubits here and say which qubits have to talk to which other qubits, and try to embed that graph in 2 dimensions or even 3 dimensions if you can make a 3-dimensional physical architecture.
Yeah. Right. So that was my question. So once you take into account the embedding of the expander in your local graph, what happens to the overheads?
Yeah, so I don't think anybody's worked that out in the case of these LDPC codes. Now I should say that it's not impossible that something could work. I mean, I don't know how to do it certainly, but if you think about concatenated codes, which was this kind of old-fashioned fault-tolerant protocol, they're not LDPC codes. Every qubit in principle has to talk to many other qubits, but because they have this hierarchical structure, you have some things that you can make local, which is the lower level codes. And then you have some higher level structures which require longer distance communication, but it doesn't have to happen very often. So it could be that if you come up with some kind of clever way of stratifying the checks in this LDPC code, you'll have some ones that can be local and have to be done frequently, and some ones that you still need, but can be done more infrequently. And maybe in that case, you could do it without any extra overhead. But again, that's just pure speculation. There's no particular reason to believe that's possible.
And in addition to overhead, it sounds like what you're saying is that it could also help you deal with, you have to do the error correction often enough, and you're saying you could defer some of it.
That's right. So you have to do some error correction frequently, but maybe you don't have to do all the error correction all the time.
Okay, great.
Okay, so I see a hand from Ike, who I guess is on the panel.
Hi, Daniel. Maybe this is a quick question. I was musing about finding LDPC codes or quantum ones. Classical LDPC codes, as I understand, are linear codes obtained from sparse bipartite graphs. And I was wondering if it's a given that quantum LDPC codes also must be linear or stabilizer codes, or could you take 2 classical LDPC codes and combine them in a way which is not going to give you a stabilizer code, but still is a useful quantum LDPC code?
Maybe. I mean, again, I don't know how to do that. But as I said in response to Ramos's question, people have thought about ground states of Hamiltonians, local Hamiltonians as codes, and maybe using that picture, you could find some way of combining them. I don't know, maybe.
I was thinking of the CWS construction, codeware stabilized states.
Yeah, maybe that might be another framework for doing it. Yeah, I mean, it's not obvious how to do that, but it possibly, yeah.
Nothing rules it out as far as you know.
No. I mean, in terms of ruling stuff out, I'm not sure there's really anything that's known. I mean, obviously there are some limits, right? We have limits on stabilizer codes in finite dimensions, for instance, but once they start to be non-stabilizer codes, the bounds are much weaker.
Right. Great. Thanks for a nice talk.
Great.
Let's see, and I see in the chat a question from Ronald DeWolf. Can you say a bit about correlated errors on multiple qubits? When does this invalidate the threshold theorem? So, so if you have correlated errors on, say, pairs of qubits, the threshold theorem will still work. I mean, it's still not a good thing because the value of the threshold will be lower. But as long as you have correlations that only affect kind of a constant number of qubits at once, then you're fine. Because you can always get that same constant number of qubits happening with a constant probability, right? Because you have 5 qubits. What's the probability of all 5 of those qubits going wrong? Even if it's independent, that's like p to the 5, which is a constant because p is constant. So it only really starts to be a problem if you have large numbers of qubits, and really they have to scale with the system size faster than log n, that have a correlated occurrence where they all go wrong at the same time with, say, a constant probability. And once that starts to happen, then you're out of the regime of where the threshold theorem works. If it's a very, very specific error model, you might still be able to do something. But in general, error correction is not going to work, and fault tolerance is not going to work.
So is it does it relate to the percolation bound then? Is that what one should be thinking of as the
Yeah, probably that's fair. What I was saying is a kind of a general thing that's not about LDPC codes. It's about error correcting codes and fault tolerance in general. But if you're dealing with LDPC codes, yeah, so your correlations are kind of having multiple things occurring at once. If they're localized, and so Todd Brunn is saying this in the chat. If they're localized, then it might be okay. But if the cluster of errors that occurs at once is very big, then of course your clusters in the percolation will be very big as well, and that will kind of overwhelm your code's ability to correct. Okay, another question in the queue, and Todd. In practice, as you mentioned, we may not need to scale up to blocks of unlimited size. If noise rates are low enough that a moderate size code block has a very low rate of uncorrectable error, we could just, okay, this is I guess a comment rather than a question. We could just scale up our computations by using multiple copies of that block instead of going to larger blocks. Could ease, though not eliminate, the locality constraints. That's right, yeah. Okay, let's see. Looks like we have a question from Amina.
Yes, so it's also maybe just a comment, but there was a question that you mentioned about density evolution, and I didn't even see it. But so what density evolution is sort of a subdecision decoding. So if it's hard, so in a classical world, you have zeros and ones, and as the algorithm progresses, some of these zeros get flipped into ones, and hopefully you converge to a correct string of bits. Now, if you have soft beliefs, then you have some density evolution. You believe that one bit is 1 with probability 1/3, another is 1 with probability 2/3, and so on. As the algorithm progresses, this density evolution becomes, you firmly believe into something, right? So it becomes zeros and ones. Okay. So is that even possible for quantum?
Well, so this is the sort of thing that doesn't work if you just take it like that in the quantum case. And the reason is because these degeneracies effectively create correlations between the errors on the different qubits, right? So because errors on these 2 qubits are the same as errors on these 2 qubits, you can't kind of treat them independently. You have to treat them collectively. And so the algorithm that I mentioned for the expander codes does this. It looks at clusters that are kind of the size of the correlations and tries to all the possibilities there. And since it's an LDPC code, they're constant size clusters. But if you look at just individual qubits, that's when you get into these cycles, and it doesn't converge anymore. So there might be something like that works. Some of these better algorithms kind of combine this small group with belief propagation type things, or this sort of density evolution. Certainly the ideas are useful, but you have to modify them to make them work with these quantum codes.
Thanks.
Okay.
Great. So let's see if there aren't any other quick questions, and let's thank Daniel again for a fantastic talk, and then we'll meet up at Gather Town. So if you'd like to meet, I put the link in the chat. So great. Thanks everybody, and thank you, Daniel.
Thank you.